Why 10.5 moles are deposited there is that we have 21 charges, and the total number of electrons that we need to discharge 1 mole is 2. So it's like you are buying something for 2 naira or for $2 or any currency, and you are having 21 naira. How many can you buy? That's like what the question is saying. This one is like 1 naira because sodium will require just 1 electron. So that's what I'm trying to say, that electron is the currency that we are spending here. So if I need 1 electron here, and for me to get 1, so if I have 21 charges coming, it will give me 21 moles, because 1 mole 1 charge, 1 mole 1 charge, it will give me 21. But what about here? It's like 1 is 2 naira, and I'm having 21 naira. I can only get 10 and a half, 10.5 of that thing. The same thing happens here. I will also get 10.5 moles here. But what about the case of aluminium? Every 1 aluminium is 3 naira. So that means I am having 21 naira. So the 3 electrons that we need for 1 aluminium, and we are having 21 electrons. How many aluminium can we get from this 21? You can see that we are going to get 7 moles. So what we are saying here is our second law. With this thing that we have said now, you can see clearly that the amount deposited there is 21. The amount here is 10.5. Amount here is 10.5, and the amount here is 7. What determines the amount of moles or the amount of elements deposited is the value of charge on each of the ions. You can see that the more the charge on the ion, the less the amount deposited. It's like the more expensive something is, the more money we need to spend on it. But if we now have the same amount of money, and you want to buy okrika and you want to buy original, you will see that the amount that you can buy with the amount of okrika you will get will be plenty, but the amount of original that you will get will be very, very minimal. So here I need 3 for just 1, but here I need 2 for 1. Here I need 2 for 1 as well, so I will get the same thing. But here I need 1 for 1, so I will get plenty. So you can see now that the amount of elements deposited is inversely proportional to the value of charge on each of the ion. This is the statement of the second law. So that is why the second law of electrolysis can simply be placed as the amount of element deposited, or we can just start by saying when the same quantity of electricity is passed through different electrolytes that are arranged in series, the amount of element deposited in each of the electrolytes is inversely proportional to the value of the charge on each of the ions. So therefore, I can now say the amount of the element deposited, which is number of mole, is inversely proportional to the value of the charge on each of the ion. Let me use small q to denote that. You can use small e if you like. So if I am able to say this, so let's go to the other side. If I'm able to say that, I can now say that the amount of element deposited, which is number of mole, is equals to, or is proportional, inverse proportional to the value of the charge on each of the ion. So what is this small charge on ion of sodium? Is going to be 1, because that's the amount of charge on the ion of sodium. Then what about if they are telling me about chlorine? The charge on chlorine is also 1, but because chlorine is a diatomic molecule, the molecule of chlorine is a diatomic gas, so that means we are not going to say Q is 1 here, but Q is going to be 2. What about if we are working with calcium ion? What are we going to call Q? Our Q is going to be 2. But what about when we talk about aluminium? So we are going to see that here our Q, small q, is going to be 3. This Q can now be called the oxidation number, or the oxidation state, or the valency. Then what about if I am talking about ion 2? You know, ion have variable oxidation states. We have ion 2 and we have ion 3. If I am having ion 3, the Q is going to be 3, but if I'm having ion 2, the Q is going to be 2. What about if I am having copper 1? Copper 1, I am going to have Q to be 1, but if I'm talking about copper 2, I am going to say Q is 2. So most times when we are given question and they just say copper, we take our Q to be 2. So let's finish the equation that we have started. But before then, let me tell you about one that is somehow corny. If we are talking about hydrogen ion, this hydrogen, it requires one electron though, but hydrogen is also a diatomic gas. So that means that one electron will not be enough when we hear hydrogen. It's going to be 1 and 1, making 2. So Q is 2 whenever we hear hydrogen gas. Then what about when we hear oxygen gas? What comes to your mind? What do you think Q is going to be? Now, in the case of oxygen, it's a group 6 element with atomic number 8, which is equals to 2,6. This person requires just 2 electrons to make 8 here. So it's going to gain 2 electrons and become O2 minus. Because of that, every oxygen needs to drop these 2 electrons. So if I am talking about oxygen atom, it will have been 2 electrons. The Q will have been 2. But when they say oxygen gas or a molecule of oxygen, this our Q is going to be these 2 and another 2, making O2. And this is going to give us minus 4. So the small q for oxygen is always 4. For hydrogen is always 2. For chlorine gas is always 2. For iron 2 is 2. For iron 3 is 3. For copper 1 is 1. For copper 2 is 2. So let's now complete the equation that we have started. If number of mole is now equals to, let us introduce a constant now. And in order to honor Michael Faraday, we say that the constant should be called F. And that F stands for Farad. So if F stands for Farad, then I can now have the number of mole to be equals to F over the value of charge on the ion. So in that case, we are having 3 terms in this our second law of electrolysis. If you have 3 terms in our second law of electrolysis, number of mole, Farad, and Q, which is the charge on the ion, which I can also call oxidation state, combining power, or oxidation number. This our number of mole. Question can come from it, and this is how it comes. We can use another formula to come into number of mole by saying number of mole equals to mass over molar mass. Number of mole can be equals to volume over molar volume when I'm dealing with a gas. Number of mole can be equals to concentration times volume. This and another one is number of mole equals to number of particles over number of Avogadro. These are the ways through which they can ask us questions from the number of mole. But when they want to ask us any of these people, they will give us Farad, they will give us the charge on the ion. Then we can get number of mole. We can now think about the formula. If they ask me to calculate mass, I will use this one: volume, concentration of volume, number of particles, or number of Avogadro. I'll use this one. Another place that question can come from is this place. It's a bit complex as well. You see the Farad that I told you that is here, Farad is like unit of money. You can see that in this world today we have plenty unit of money, but one of the best that we have is our own naira. Okay, they play. Though you have dollar, you have pounds, you have yen, you have different currencies. Before Michael Faraday did this, somebody already gave us a unit for quantity of charge or quantity of electricity, and that was the Frenchman that we call coulomb. So the actual unit of quantity of charge is coulomb. So meaning that if I do my calculation and I get Q to be equals to IT, what I have gotten here, the unit is always coulomb. If I now have coulomb, I should not use coulomb in Faraday's law. I should use Farad. That's how we honor Michael Faraday. That means that if you want to spend money in Nigeria you cannot spend dollars, you can only spend naira. This is how we do here. But if you are going to somewhere else, you can change naira to dollar, you can also change dollars to naira. So it simply means I can change farad to coulomb, and I can also change coulomb to farad. But if I'm working in this equation, I can only use farad, I must never use coulomb. So on the day you are given current in ampere and you are given time in second, if you are not given second, you take it to second. What you will get from here is Q, which is measured in coulomb. When you get your coulomb, don't put it in this formula. Divide that your coulomb by the value of 1 farad, which is 96500. If you want to go, if I want to go from coulomb to farad, I am going to divide by 96500. It's a constant that they always give us. So by the time I do this division, my answer has been taken to farad. But what about if that's not the case? What if you are given every information to get number of mole? You are given this Q, and then you are asked to look, you are given current and you are asked to look for time, or you are given time, you are asked to look for current. You can see what you are looking for is in farad. So cross multiply, get your farad. When you have your farad, you will now say that, okay, farad can now be converted to coulomb. How will I convert farad to coulomb? The answer is that I will multiply by 96500. But if I want to take coulomb to farad, what will I do? I will divide by 96500. So this is how we do the conversion here. So you can see that second law is all about comparison. That if I pass the same quantity of electricity through different electrolytes, what will happen? Then the man told us that the amount of element deposited in each of the electrolytes depends, and not just dependent, but also inversely to the value of charge on each of the ions. So now we are done with everything that they call electrolysis, except for one thing that I did not really go deeply in, and that is the idea of the factor that will affect the discharge of ion during electrolysis. That one is a bit complex, so I will explain that in another lecture. But in this lecture now, we're going to solve all the questions that are involved in electrolysis in our part 3 of the work.